the encoder had two parts, a source encoding and a channel encoding. Now you might argue, as we will ultimately, that you could do it better in one step, but what we normally do is source encode to a standard interface, a binary, and then we encode for the channel. The reason is, on one side we can take very many different inputs, on the other side we can use very many different kinds of channels. And we can keep the two problems pretty well separate by working to a common interface. We are still looking at the source. And what we did last time was to show you that the code efficiency, namely the average code length, depended upon the probabilities. How probable were various symbols? What you want, of course, is the short symbols to be the high probability ones and the long symbols to be the low probability ones. Well, the question is, how do I find the best? How can I find the best code given the probabilities? And this is a question that Huffman asked himself. He found a solution, but I've got to derive the material why it works. So I will suppose the probabilities are in one order, and the lengths now it's intuitively evident, but if you want to prove that they should be in that order, we'll suppose that for a couple of P's to L's, they are not in that order. So in the original sum, there will be Pm L sub m plus P sub m plus 1 L sub m plus 1. Now if they were not in that order, I'm going to interchange the two symbols L, one L and the other, and the new one I will have Pm L m plus 1 plus Pm plus 1 Lm. Now if I subtract minus new, I will have, I claim, Pm minus Pm plus 1 Lm minus Lm plus 1, I think. Let's see, there's a Pm Lm, there's a Pm plus 1, Lm plus 1 with a plus sign, and the other two cross terms are this. Now if the PLs were in order, and these were in the same order, the number would be negative, and I would have gained by interchanging two symbols. So I assert it's fairly evident, just intuitively, that this must be so. That I can take the ones in one order, take the others in the opposite order. Well now, the problem is still, how am I going to do it? The last thing I have to observe is that there, in the decoding tree, there are going to be two symbols of the maximum length. If there weren't, if there were a decision here and only one of that length, why bother with the decision? You already know, right? So there's going to be two. So Huffman said, take the last two symbols and combine them. And I'll do the case that he did in his paper. P1 is 4/10, P2 equals 2/10, P3 equals 2/10, P4 equals 1/10, and P5 equals 1/10. He says take these two and combine them, and you will have 4/10, 2/10, 2/10, and 2/10. I'm going to combine them as a single symbol. What I'm doing is combining these two symbols into one symbol here and putting it here. Now, he says, I have a same problem we did before, but one step smaller. Let's do it again. 4/10, 4/10, 2/10. Let's do it again. 6/10, 4/10. Now, anybody knows how to encode efficiently two symbols, 0 and 1. Well, that 1 came from here, so I put the 1 here, and I just take it back here, and this is going to be the symbol 1. This 0 came from 2 places, so I'm going to write 0, 0, 0, 1. The 01. The 00 was split, so I've got 000 and 001. This comes back here, 000, and this 001 becomes 0010 and 0011. And these are the symbols. You've got the lengths, and that will turn out to be the most efficient. Now, the argument is simply, as I go forward, if this were not the most efficient coding, consider one which was more efficient. When you examine the step of going forward, both this one and the new one are reduced by the same amount. If there were a better one than this, you would come down to this position, able to do it in less than an average length of 1. But given 2 symbols, you can't do it less than the average length of 1. So the conclusion is, this is optimal. And it rests on the fact that when I go down, the reduction due to this combining will be the same for any encoding you have. Therefore, this will turn out to be the best. This tells you the very important problem. How do you do it? How will you get the thing? Now, I want to point out to you I could have done something different. So I will do the same thing again and show you what an underlying problem is.
Couldn't you take the last 2 codes for the P4 and 5 and just drop the first 0 and you've reduced their length both by 1, yet you still have 5 unique symbols?
No. What I have is this one is a prefix of this one and that one. Right? I don't have unique decodability. Okay? Because that symbol, or this one, this symbol could also be P2, P1. So I lose unique decodability, okay? Fine. Everybody aboard? Not a bad observation. Now I got to get a black one first. I'll write them down again. 4/10. If this time I put it 4/10, I put it as high as possible. What will I come up with? Well, 0, 0, 1, 1, 0, 0, 0, 1. 1, 0, 1, 1, this is 0, 0. This one is 0, 1. This is 1, 0, 1, 1. And this 0, 1 becomes 0, 1, 0, 0, 1, 1. This will have exactly the same average code length as this. This is much bushier. It pays the price here, it gains it back here. Well, I knew this, and when a student came around for a thesis one time, I suggested, what would be a property that you would like to have of all the equivalent codes, which is best? Well, the one with the least variability will have the property that in encoding messages, long ones will tend to be long, short will be short, but if there's great variability, some short message will come out very long, and that won't be very nice. You'd rather have a system which you pretty well knew how long the message was going to be from the source code. The reduction of variability would be a great idea. Well, if you do as I did here, and put it the highest point each time, you reduce the variability greatest, because by pushing it up as far as I can, it goes through less splitting stages. I have fewer long ones, I have more of these, I have less variability here than I will have over there. And indeed, if the probability is a little less let's see, when we're up to here, up 4. If that were a little less than 4/10, if I put it above, I would pay a very small amount in the average code length. I would gain a lot in variability. Now this is a general engineering principle. If you have an optimum, normally it's fairly broad. This is the property you want. Your gut found the optimum design. If I move a little bit one way or the other, I get a great change in that variable, but I pay very little in performance. It's a general principle of engineering. When you optimize a design, ask yourself, yes, it was optimal that way, but are there other characteristics I might want? In particular, is it like Hamming is drawn here, that I can make big variations in the parameters, some of the parameters, and not affect performance, but gain other properties, like in this case I'm telling you, giving up, putting sometimes one slightly above where it should be, reduces the variability enormously and increases the average code length very little. It's a general engineering principle. Well now, since Huffman is an important code, I'm going to do one more for you, so I'm sure, well, I'm reasonably sure you know how to do it. So I made a bunch of probabilities. A third, a fifth, a sixth, a tenth, a 12th, a 20th, a 30th, and a 30th. It's a big enough job. Well, fractions are hard. I can look, and since I made up the problem, I know that the common denominator is 60, right? Okay, I'm going to convert them all to 60ths. This is 20, 12, 10, 6, 5, 3, 2, 2. 32, 42, 48, 53, 56, 58, 60. I got them all right, right? I can work in these numbers instead of these because it's only comparing bigger or less, right? All right. This is 20, 12, 10, 6, 5. There's 7. It's got to go up to here. 20, 12, 10, 7, 6, 5. 13. 20, 13, 12, 10, 7. Sorry? I got a mistake?
6 and 5 are new.
12.
It's not 13. Second one down on the line. Yeah, 6 and 5.
Here. 5, 6.
No, 6 plus 5, the other one goes
Combine 6 and 5 over them.
Well, we'll find out easy enough. 33, 45, 55, 60. You're right. There's an error.
Yeah, 5 plus your second one is last
6 plus 5 is 11.
5,
next.
11. Yep. You're right. Okay. All right. Now we've got 17, 12, 11. 33, 20, 12. Oh, well, I don't mind. Now, what will I do? I'll put a 0 and a 1. Every time I hit a split, I copy the digits down and put a 0, and copy the 0 and put a 1, right? Now, let's look at this process. Going forward, it's mechanical, and it's the same iterative program each time. Correct? Going back, if you will record the number, which was the sum, just put them down here in a list. You pick this one, you know which one it is, and you work your way back. So the backward process is mechanical too. Thus, it is easy to write a program which will encode data and decode it. What you have to have is the frequencies. And there have been programs written for important storage problems which go through and find the frequencies, or approximate frequencies, call up the code, encode it. You ship over to the recipient the decoding tree, and then the code. As a result, for example, when I came here, they were working on earthquakes versus atomic bomb explosions, the vibration of the earth. They had lots and lots of data. By building a program which would encode like this, they cut down the storage problem enormously. And you can see when you come back out of backup data, you only look at one bit like that, one at a time, and the thing is decoded. So that if you are in a situation where you need compression of data, Huffman code tells you the best you can do. Now I'll tell you some simple rules about Huffman. If all the probabilities are the same, and I use the second trick, you'll come up with essentially a block code, all of the same length, but a few of them maybe a little shorter. If it is true that in these probabilities, the sum of these is less than 2/3 the next one, then you'll get one of these comma codes of the type 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1. That's a comma code. You get a code like that. Block codes don't save you anything. Comma codes do. If I calculate that whole thing out, I will get a length about 2.58, I think. But if I tried to code those in a block code, I'd have 3 bits in every one. The average length would be 3. So the Huffman code would save about 5/10 of a bit per symbol. The more variable it is, the more Huffman can give you. And if you have a lot of data with lots and lots of zeros in it, then you can gain a great deal from Huffman. If you have pretty much uniform, you can't do it. You won't gain much. So Huffman is the answer to the question, and it's easily done. It's mechanical, how to encode and decode. And in fact, you will find shipping over the decoding tree together with the encoding will save channel capacity and storage capacity. And coming back, the decoding is you look at a bit like that, and out come, as you come out the leaves of the encoding tree, out come the symbols. It is not terribly hard to do. It does not slow down machines enormously. Of course, right in the middle of calculation, you don't do it, but when you have to store things, particularly if you have to store a thing for years, it pays. Otherwise, it doesn't. Now, I want to go on and talk about the other side of the problem, namely the channel encoding. The channel's got noise. What can I do? Well, let's start more or less where I started. I met 2 out of 5 code. C52 is 5 times 4 over 2 is 10. The 10 decimal symbols were represented in a telephone company by 2 relays out of 5 being up, or sometimes 3 out of 5, depending which code they wanted. You recognize the 2 out of 5 and 3 out of 5 code are really the same thing. It's a question whether you have them up or down. And you can see that if one relay fails, or one relay closes when it shouldn't, there'll be an odd number of relays. Well, it didn't take me long to realize that if I have a bunch of bits, n minus 1, I could add one more bit for an even number of ones in the whole message. The whole message now will be length n and an even number. So I send the bits to you. You receive them, even number, fine. Odd number, something is wrong, right? It's evident. 2 errors you won't catch. So we have to look at the question of what are the probability of errors. Now if I have a very short message and the probability is low, the chance of a double error is very, very low. If I make a very long message, the probability of 2 errors is kind of high, right? On the other hand, I'm getting more for the extra 1 bit that I'm having to send, which is wasted capacity. It's capacity, channel capacity, but you're wasted for reliability. So you want long ones to cut down the redundancy of the extra bit. You want short ones for reliability. So you want the probabilities. So you say to yourself, well, that's not hard to get. We know a little bit about probability. We don't need to know much. That's 1 to the nth power. But if I expand this out, this is 1 minus p to the nth plus n, 1 minus p to the n minus 1 p plus n minus 1 over 2, 1 minus p to the n minus 2 p squared, and so on. This is a probability of no error. If p is a probability of error, 1 minus p is a probability of no error in 1 bit, n of them independent bits, and that's the one I'm going to assume. I'm going to assume for the moment what we call white noise. All probabilities are the same and they are independent. Now, that isn't really true. Lightning strikes, there's induced currents, and you're likely to get several bad bits. On a tape, the bits near the edge are likely to be misread because the tape has been stretched more on the edge for one reason or other than it would be in the middle. If the power supply of your machine fluctuates a little bit, the errors are not independent, correct? Nevertheless, on the average, we attempt to achieve that by various devices. We often put the computer on a floating battery. We charge the battery, as does the central offices and telephone company. We charge the battery up and we power it from the battery. When the source goes off, the battery is still there, delivering for some time. And if you have to stay up, then you go downstairs and yank the cord on the emergency generator and get it going in place of the failed power supply, which is what the telephone company always does and which computers do. You can get them. In fact, you can get them with a very small power supply. I was connected with a computer company for a while on the board of directors, and one of the things we did is we sold an extra package for not a great deal of money, which had a condenser only. And we could, with the time that condenser held enough charge, store all the volatile information and quit. When the power came back on, we first reloaded from the permanent memory back the volatile material and resumed. And so fluctuations of power you would not even notice. A very simple device. It can be done many, many ways to keep a power supply going in spite of power failures of the source. Well, this is the probability of 1 error. N minus 1 correct, 1 wrong, and in any one of n places. N minus 2 right, 2 wrong, and in any one of n minus 2 places. The next one, n minus 3, and so on. And you see this p being small, 1 minus p is close to 1, np. If that's near 1, you're in trouble. If np is small, we write very small by inequality twice. Then each time I'm picking up an np, this one I got another n and another p, and I got a 2. Next one I'll get another n minus 2, a p, and a 3. So you see that the higher errors do in fact go down when the product np is reasonably small. And that's your engineering problem. How much do you want to pay for the extra redundancy for the risk of this double error, which you cannot find? It's an engineering judgment. It balances the likelihood of being wrong with the likelihood of being efficient. And nobody can answer that question for you except in a concrete case where you tell me exactly what's involved both sides, then I can do it. So here is a generalization of this. And later on I looked in and there was a 3 out of 7 code. in telegraphy? Well, that's C73, which is 7, 6, 5 over 1, 2, 3, which is 35. That will have 35 symbols. Now, once I saw this, I saw that they were missing none out of 5 and 4 out of 5. They had both those possibilities. There were 5 4 out of 5s. None out of 5 was only 1. There were 6 symbols they were not using. They had wasted capacity. But this idea of how to find a code that will catch errors. Now, what do you do when you find an error? You can repeat. You can ask for, hey, there was an error, send it again. But that involves two-way transmission. That was what's often done. In telegrams, if there's a risk of error, the telegram will often have at the bottom underlined, will not, or will. They're afraid of an extra word getting caught in someplace, misunderstood. They were repeating right with the thing. Now, if you had a tape, as we had on the IBM 701s, which occasionally made mistakes but had errors in the blocks, you can repeat. Now, if the bit was marginal, on repetition you're likely to read it correctly, you'll come out. But if the bit was very bad, you'll keep on repeating until another bit is bad, and then you'll have 2 of them wrong, and you think you're right. So whether you try repeated reading or not in the presence of an isolated error depends upon what you think the nature of the error is. If you think it's a marginal error, you'll catch it next time probably. But if you think it's a genuine, all-out error, then repeating until you get a right message is waiting until you get 2 errors, which is bad strategy. So it raises some questions which you have to think about what you want to do. It's not obvious, although we started doing things foolishly for some years. Now, I'm going to talk about something else which occurred out of sequence, but is typical of how things happen, and it reveals a good deal about how I operated. The next lecture is on the subject of how can I go further? If the machine has an error, why can I locate where it is and change it? And I became famous for this. And the episode happens, I'm going to tell you, after I became famous for this, but somebody from AT&T said, we have a code of letters, 26, numbers, 10, and a space. Think of inventory if you wish. You know how many inventories have numbers and spaces and letters stored around? Well, they said, how should we encode it to catch errors? Because we're making too many errors. Humans are dealing with it, making many, many errors. Now, what did I know about humans? Now, it's easy. From having computed and having run a group of desk calculator girls myself and seen their errors, the errors that humans make as against machines are rather different. Given 667, that's likely to come out. And if you watch when you get wrong numbers on your phone and ask, what number did you want? You'll find that's a very, very common error. The other one is 6-7 goes into 7-6. You reverse a pair of digits. That's a very, very common one. But that, you see, is 2 digits wrong, right? Evidently, that kind of error I could not cope with. What could I do? I assert, the sensible thing. I got the 2 smartest guys I knew, one was more practical and the other was more theoretical, into a conference room with me and posed them the problem. And they came up with a suggestion. I looked at it a while and said, not good enough. Not good enough. Not good enough. Until Ed Gilbert, one of them, says the following. What we're going to do is, to these symbols, we're going to assign a number 0 up to 36. And you're going to calculate, let's call this xi. It's the number associated with the ith symbol in your message. K x sub k. modulo 37, which means divide by 37 and the remainder should be taken. Now, if you look at this, you see that this error changes one digit, and I will change a product k times that. And that's not going to be divisible by 37, because it's a product of two numbers and 37 is a prime, right? If I interchange two of them, whether they're adjacent or not, if you examine what will happen, if I interchange a pair of digits, even if they're far apart, unless they're 37 apart, you see the sum will change. The sum will be changed. Well, here then is a code which I'll call a weighted code. Weight the symbols, take the number values of the symbols, whichever numbers you want to assign. For example, this could be numbers 0 through 9 for the 10 digits. That could be the 26 letters running from 10 to 35, and 36 could be the space. Any number you want assigned to it. Calculate that and pick the first digit, the xk with a 1, to be the one which makes exactly 0. Use x1 to do it. Now you say that involves a lot of multiplications, but it doesn't. I will show you a simple trick that's known for a generation back, but you probably don't know it. I'm going to add them up. And now I'm going to add this column. X, 2x plus y, 3x plus 2y plus z, 4x plus 3y plus 2z plus w. I'm getting exactly the weighted sum by miserable additions. Right? I don't have to have any powerful machine. I can do it. So I can do this trick. I calculate all the numbers but the first. I leave this one 0. I calculate, divide by 37, I see what remainder I have. I take the complement of that and put it in the first position, and then the sum will be 0. And I will have a message which I can ship to you. Now this is widely used. You remember you have ISBN numbers on your books. Remember those things in the back? Forget the dashes. There's something at the end, a dash, something added on, right? They wanted to use a code just like this, but they only want to use digits. There were 10 digits. 10 is not a prime. So they made it 11. They did it not mod 37, but with only digits, they made it mod 11. And every once in a while, when they had to have an extra one, they put in the symbol X. So about on every 11th book you own, that you bought recently, the last digit will be an X. And you can try out in your numbers. There's simply exactly this kind of a code here, weighted code with the last one tucked on to fit. So your total amount will come out. And that way, when you send a book number, if there's an error, they can catch it. I want to dwell on this matter very much. The first error correction I talked about was what I called white noise. It's the machine type of noise. It copes with the problem. This I'm talking about is human noise, which is different. It's this kind of nonsense here. And some other ones. But those are the two overwhelming errors. The other error made in dialing in the early days was 0 and the letter O. That was another common error dialing. But nowadays, we put a line through the 0. So we're pretty well protected against this. Now I tell you the following simple thing. If you were to put this kind of a code, which is easily calculated, on inventory parts, which are typically of this type, then the moment that order hit a machine, it could be checked. Is there such a part? If somebody has made a mistake, it can be caught. Rather than having the damn thing go all the way up to supply look around and say, there isn't any such a part, or shipping the wrong part, and you coming back either with the wrong part or a great delay. Adoption of such codes as this, when dealing with humans, is enormously protective for the cost of one extra letter. The ISBN number is a good example. They put on one more character for the book number. Now, if you want to know what digits are, the first one I think is the language, the next one is the country, the next one is the publisher, and so on. Those dashes they put along the way are merely to help you read country, language, and publisher, and then the publisher's numbers, and then the parity check at the back end. These kind of things can be done. I want to dwell on the subject of how much I have not talked about. When I thought about the problem of codes, having lived through the computer business, I recognized there were an enormous number of codes devised by varying people to do varying things. For example, in representing decimal digits, Aitken on relays used the binary form with 3 extra, because there are 16 binary numbers and only 10 decimal. He had the property then that the complement in binary was the complement in decimal. There are lots of different codes. I've been involved in a great many of them, but I know of no really broad principles that I can give you for covering all the other codes floating around. I've given you the essential features. Huffman Code tells you how to be efficient, but this kind of a code like this is something a clever guy has to think up. But you people are presumably clever. When you meet some new noise, not human and not white noise, then you have to, if you're really going to do the job well, invent a corresponding code. There's a saying, you got to know the enemy. Well, you got to know what the noise is before you can do it. There is an enormous field out there, but it is probably easiest for you to learn to think for yourself and think of what the principles are, and when you face a situation, design a code to meet your needs. And I say again, the adoption in inventory of a weighted code. You'll only be out in the field for a while and find the wrong part shipped to you, or headquarters phoning back after some time filling around. We haven't got any parts. What did you want? Huh. The person who gets the message doesn't know. He didn't write out the order. So it takes a long while to find out the person who wrote the order. On the other hand, as tight as you want, you could, if you made the people write out the order on a machine as the order was being written out. Out would come a thing, no such part. Read the catalog again. And the guy, oh, and proceeds to type in the right part. Now that won't cure the fact that somebody said, I want part A, and the person ordered part B. I can't stop that kind of human. But I can stop the carelessness of probably an error in reading the digits. And the book publishers found it so difficult that they went to exactly the same kind of code, and they went to a base 11. It has to be a prime number to get away with it. Because so the product of these two numbers can never be the modulo. And once you have that, any change will no longer leave it divisible by 0. The interchange could, if two numbers were 37 positions away, you could of course change them because their weights would be that way. But the chance of two digits exactly 37 apart being interchanged is extremely low. So it catches most errors, again, single errors. It does not catch double errors, and it doesn't really tell you where it was. So we've got plenty of time. I trust you know where we are. The next lecture on error correcting codes is really 2 lectures. It's my attempt to tell you how I found them, and also to tell you what they are and how to do it. Just as I showed you Huffman codes to the point where you ought to be able to do one if you need it, perhaps with a prompting of a book here or there, but you ought to be able to do it. The same way I'm going to try and get you to the point where if you had to, you could manage to figure out how to do a Hamming code. And as I told a friend of mine the other day, I have for years, after giving a talk, pointed my finger to class and said, does anyone dare stand up and say they couldn't have done it in my place? That's what's going to happen next time. At the end of the lecture, I'm going to stick my finger in your face and say, are you prepared to say you could not have done it in my place? Now, I'll give it to you the whole lecture in less than 50 minutes, and I had months to do it. So it's not a question, you do it on the fly the way I'm doing it in class, it's a question of how much. And one of the motivations is to show you how simple creativity is. Another is to convince you that you yourself could do great work. So the next lecture is a rather peculiar lecture. It's got these two goals in mind, and it's concerned with the channel capacity. And it comes down from the remark I'll repeat next time. While using this error detecting machine, which would go back and repeat the problem a couple times automatically, and if it couldn't get it done, it would then go on to the next problem, and it got me in trouble. I, in some anger, said, if the machine can locate where it is, if it locate there is an error, why can't it locate where it is? Because if I know where it is, I change a 1 to a 0 or a 0 to 1, and I'm in. Now, I admit that I didn't say it quite in those polite words. I said rather stronger words than that. But fundamentally, that is what happened. And I decided, that's a sensible question. Let me look into the question of how I can get a machine to locate where an error is and therefore correct it. The same way in a message I send to you. Now, these are used enormously now. I started a thing, and following a strategy I've always used, I went on to do other things. There is a tendency for somebody to create something good and spend the rest of life doing it. And if you want an example, we got good old Al Einstein. He got some unified theory, then he spent the second half of his life, more than the second half of his life, producing nothing, trying to continue. I have seen any number of people do good work, do something great, and then spend the rest of life elaborating that great idea. It's a waste of talent. I didn't want to become the person who knew everything about one small thing, so I consciously and deliberately set it aside and tried to do something else. And then I'm really talking about the theme which the whole course is about. How do you learn to manage yourself so you will have a highly productive creative career rather than just the ordinary one? After all, some of the students out of here are going to turn out to be chief of staff, and most of them aren't. My simple problem is, how do I increase the probability of the students I have ending up as chief of staff, or general, or admiral? Very simple. Also very hard, so I'm depending upon you. So come in tomorrow, for sure, 3 o'clock.